of my former student, Jeffrey Zhang, who's now in the math department at CMU, and actually probably about to move soon. So the motivation for this talk is, I hope, pretty clear. And as we move to more and more non-convex optimization problems as a community, motivated by some of the modern applications, of course, there becomes a distinction between local minima and global minima. And we have a fairly good understanding of the complexity of finding global minima in various types of optimization problems. But a very natural question is, okay, for problems for which it's hard to find a global minimum, is it easier for us to find one of the possibly many local minima? And I want to give a rather complete answer to this question in the case of polynomial optimization problems. As we will see in the talk, there will be sort of two critical cases where this question needs to be studied, and these are the two parts of the talk. For the first part, I will give sort of a complete analysis and a full proof. And the second part will be much shorter, where I just sort of announce the results and give some intuition, because the proofs of the second part are a bit more technical. Okay, so let me just formalize what the setting is and what the question is. So first of all, if you're minimizing a function f over a subset of Rn, as a reminder, a point is a local minimum. First of all, if it's feasible, and then if there exists some neighborhood of positive radius, this neighborhood can be as small as u1, it just has to have a positive radius, such that if you compare your candidate point to other points in this neighborhood which are also feasible, then your point has a better objective value, or it has objective value no worse. Right? So it's a much weaker requirement than global optimality, of course, because you just want to beat your neighbors, not everybody else, which is feasible. Okay, and in this tiny example, we have these three local minima. And of course, the complexity of this question will depend on f and omega and the representation. And in this talk, I will focus on the case where f and omega are defined by polynomials. So f is a polynomial and omega is defined by finitely many polynomial inequalities. They're exactly polynomial optimization problems. And this is a sensible thing to do because, for one thing, local minima are a local notion, and on compact sets, polynomials can approximate other functions arbitrarily well. So this is a good test case. And also because polynomials are finitely parameterized, I can study the complexity of this question in the Turing model formally. So I will take as input all the coefficients of these polynomials f and gi's that are given as rational numbers. And the size of the input would be the number of bits I need to write down these rational numbers. And I have what I'm after is to find the local minimum of problems of this type. And I want to understand the running time of the algorithm that finds the local minimum as a function of the size of the input, this bit size, right? And of course, polynomial optimization, I think, is one of the favorite problems of Monique. So this is even further justification to focus on this today. Okay, so let's consider sort of the simplest cases. And typically, we fix the degrees of f and gi and study the complexity as the number of variables increases. So if you fix the degrees all to 1, then you have the case of linear programming, where the problem is convex and local and global minima are the same. And it's well known that you can find a global min, which is the same as local min, in this case in polytime. Right? So the first interesting case already appears where I keep the feasible set polyhedral. So all the gi's are still affine polynomials. But the degree of f goes up by 1, and this becomes quadratic programming. Right? And it's sort of well known that already when your quadratic function as its matrix has one negative eigenvalue, global minima are NP hard to find. But it's very natural to ask, okay, what about local minima? Is it easier to find local minima? And this is the main part of this talk. I want to give you a complete proof of the theorem that answers this question. And this theorem was motivated by this question that Pardalos and Vavasis asked very explicitly in 92. So if I read the question, it literally says what I just said, that what is the complexity of finding even a local minimizer for a non-convex quadratic program? Now I'm going to talk about why they want to assume the feasible set is compact on the next slide. But I do want to make a distinction in case some of you are familiar with the sort of well-known result of Murthy and Kabadi that they also go to explain. that there's a related problem, the recognition problem, that if I give you a polynomial optimization problem, let's say a quadratic program, and a point, and I ask you, is this a point a local minimum? That was already shown by Murthy and Kabadi that this is an NPR problem. However, as is explained here, this does not rule out that there could be other local minima that are easily verified as a local minimizer, and potentially a polytime algorithm could find them. Okay? So to make this distinction even more explicit, let's look at sort of the proof that Murthy and Kabadi gave. In case you haven't seen it, is quite simple. So if you recall what a copositive matrix is, so a symmetric matrix is copositive if its quadratic form is non-negative on the non-negative orthant. So when evaluated on x's that are entry-wise non-negative, right? And they showed that that the problem of testing copositivity is NP-hard. And once you have this, this result of Murthy and Kabadi is immediate, because if you consider the problem of minimizing x transpose mx on the non-negative orthant, and you ask, is 0 a local minimum? So the candidate would be the point 0. Well, if the matrix is copositive, your quadratic function is 0 here and non-negative here. So this is a local min. In fact, it's a global min. Right? Conversely, if your matrix is not copositive, that means that for some point x hat in the non-negative orthant, this quadratic form is negative. But then you can just draw the rate through the origin, and by homogeneity, this quadratic form will be negative on the entire line. So arbitrarily close to the origin, you will have negative values. So the origin cannot be a local min because the value there is 0. So this is a descent direction. So that's a proof that checking whether a point is a local min is NP-hard. However, the problem we're interested in is slightly different, because you don't have a point given as input. You just have the quadratic program as input. And the analogous question would be, does the problem even have a local min? Let's say if the feasible set was unbounded. And this connection between copositivity then fails. For instance, so of course, if your matrix is copositive, then the problem of minimizing x transpose mx over the non-negative orthant will always have a local min at the origin, but the converse direction fails. So for instance, this matrix is not copositive. Nevertheless, this quadratic function has a local min at a different point, at the point 1, 0. Does that make sense? So there is no one-to-one correspondence between existence of local minima and copositivity of the matrix. Okay. So the next thing I want to clarify is the precise formulation of the question. So remember, they're asking why can you find the local min of a QP over a compact set? And the reason is simply that once you assume compactness, then you're guaranteed to have a local min, right? Because by Weierstrass's theorem, you're minimizing a continuous function over a compact set. There's always a minimizer, a global min, which in particular would be a local min, and there could possibly be other local minima. But there will always be at least one. And then if your algorithm wants to find this local min, maybe the first question you need to ask is that, what will this local min have a small representation for me to return? What if local minima are irrational, for instance, or have large bit sizes? So luckily, this is not the case. So it was known already by Vavasis that if you have a QP, there is always a local min, in particular a global min, which is rational, and it has polynomial bit size. So what we're after, so this is a search problem. So we know something exists, and it has small bit size. We just want to find it. Right? It's not a decision problem. So in a sense, it's similar to the problem of finding a Nash equilibrium of a game. That is something that they always exist, and there's a search question about finding it. Okay, and here's the main theorem that gives an answer to this question. So we showed that unless P equals MP, there cannot be a polytime algorithm that finds the local min of a quadratic program. In fact, the negative result is stronger. It says not only you cannot find the local min, you cannot even get close to it. You cannot get even exponentially close. So for any constant c, fix c to be 2 or 100, there is no polytime algorithm that can return a point which is within distance 2 to the n of some local min of a quadratic program. Okay? And the main part of this talk will be to prove this theorem, and then in the last maybe 5-10 minutes move to the other case. Okay. Now, thankfully, Frank here made my job easy, at least on this slide, except that he called it an independent set. I'm going to call the same thing a stable set. So a stable set in a graph is a subset of the nodes that are pairwise non-adjacent. And the stability number of a graph, also denoted by alpha, as Frank had it, is the size of the largest stable set. So for instance, in this graph, you have 5 nodes that are pairwise non-adjacent. And you can check that you cannot do 6 vertices. So indeed, the alpha of this graph is 5. Okay? And the base of the reduction for us will be the problem of testing given a graph at an integer r between 1 and n, because alpha is obviously an integer between 1 and n, if alpha of g is more than or equal to r. In other words, does the graph have at least one stable set? Does it have a stable set of size at least r? And this is well known to be NP complete, as shown by Karp. Okay. And in fact, this is the full reduction. So what I'm going to show you is that if there was a polytime algorithm that got within distance c to the n of any local min of a following quadratic program, then this algorithm could solve the stable set problem. So what you carry over from the graph is the adjacency matrix and the scalar r, integer r. So you subtract 1/2 and you construct this objective function. And the constraints are non-negativity on the x and one last constraint which makes the feasible set compact, as requested by Pardalos and Vavasis, right? And we need to make sure this you can write this problem down in polytime. And indeed, this is the case because even though you see c to the n here, the number of bits required to write this down is n. Which is poly because we need order n squared bits just to write down a, so this is fine. And computing this thing of the square root of n is also fine. So trust me on all of this, we can write this problem down in polytime. Okay, any questions at this point? This is what I'm going to prove.
I mean, is there anything special about the bound? Like this 3?
No, is literally, you will see in the proof, is literally the largest number you can put. The larger you put here, the stronger your result, and it's the largest number you can write in polytime. So you can improve this slightly by doing like c to the poly n, but this gives a negative enough result. Yeah. So the result will be true if I put an n here, just that you don't get as good of a inapproximability result as you put this, and it's the largest number you can put and write down in polytime. It's a good question. Yes. Every c, so fixed c. Yeah, c is fixed, but you can do any number. Good question. Okay, so I'm going to prove this to a series of lemmas, and I'm going to have letters assigned to these lemmas so we can think of them in our head instead of having numbers. So the first lemma is an intermediate result, and the bulk of the proof is here, so which is about unconstrained quartic polynomials. So we're going to go to degree 4, and then we're going to come back to degree 2. And this is a decision question. We're going to show is NPR to decide, given a degree 4 polynomial, if he has a local min, right? And to prove this lemma QU, we're going to need one slide, which I put here on the board because I'm going to very frequently refer to this lemma M here. And so the departure point here is the famous theorem of Motzkin and Strauss, which relates 1 over a stability number of a graph to the minimum of a quadratic function over the simplex. In fact, for this talk, I'm not going to be using the Motzkin-Strauss theorem. I'm going to be using a reformulation of it, which is well known in the literature, and it's already in a work of de Klerk and Pesechnik, where they create a hierarchy for alpha using the Motzkin-Strauss formulation, and this hierarchy has been analyzed by Monique and Filippi here. There's certainly some connections there. But this is the lemma I'm going to be using. So first of all, given a graph, so adjacency matrix A, and a scalar K, I'm going to talk about a matrix M very frequently. So this matrix is K times adjacency plus identity minus the matrix of all ones. And then once I have this symmetric matrix, I'm going to create 2 polynomials out of it. Q is the quadratic one, and P for polynomial is the quartic one, degree 4. Q is simply the quadratic form of the polynomial of the matrix. And P, instead of x, I put the entry-wise x squared vector on both sides. So this is a homogeneous quartic, P of AK. And the lemma is the following, and this is a 3-line reformulation of the theorem. But I want you to remember that's on the board. So it says that the stability number of the graph is less than k if and only if this matrix M is copositive. So it takes non-negative values on the non-negative orthant. And if further this is strictly less than k, then this quartic form is positive definite, meaning that for a non-zero x, it takes a positive value. And this is also an if and only if, but the reason this is in gray is that I'm not going to be using this implication. I'm going to be using the other three. OK. And this is on the board. All right, so the first lemma we want to prove is that for a quartic, is NPR to test if there is a local min. And this is how we're going to prove it. We're going to show that if you're given a graph G and an integer R, you can test this question alpha more than R if and only if this quartic polynomial with k replaced by R minus a half has no local min. So the fact that I'm subtracting a half is, the half is not important. You can subtract any other rational number you want less than 1, but it is important that you subtract something, and this will become hopefully clear. All right, and this will follow if I can prove the following slightly more general statement, that for a non-integer scalar k, alpha is more than k if and only if PAK has no local min. So PAK is a quartic defined by the adjacency matrix, and then rational but not integer number k. Okay? Why does this imply that? Because if this is true, I can then apply it with k equal to R minus a half. I'm going to get that this polynomial has no local min if and only if alpha g is more than or equal to R minus a half. But because R is an integer, that's the same thing. If you're more than R minus a half, you're more than R. So this is the same thing. Okay, so now my goal is to prove this. I call it the non-integer lemma. For any non-integer scalar k, alpha is more than k if and only if PAK has no local min. So one direction is easy, and it doesn't use the non-integer fact that if alpha is less than k, then PAK is positive definite. If PAK is positive definite, x is a 0 is a local min, right? Because the form vanishes at 0. If it's positive everywhere else, this is a global min. It's definitely a local min. Okay. Now what about the converse? So now if alpha is more than or equal to k, then because k is non-integer, then I can say alpha is in fact strictly more than k, because alpha is an integer and k is not. Okay. Then I use lemma M again, the first case, and I can conclude that this matrix MAK is not copositive, right? Which is the same as saying this quartic form is not non-negative. So sorry for all the negations. Which means that 0 is not a local min, right? Because if this quartic form is not non-negative, that means at some point in space it goes negative. And again, I can connect it to the origin. On the entire line, you will be negative. Arbitrarily close to the origin, you will be negative. So 0 cannot be a local min. But have I established this converse direction? Of course not, right? Because what I want to show is that if alpha is more than or equal to k, then this polynomial has no local min whatsoever. The only thing I've done is that I've shown that 0 is not a local min. So now I need to worry about every other point in Rn, right? But let's remember that any local min must satisfy, let's call it x bar, must satisfy first and second order necessary conditions. So the gradient should vanish, and the Hessian of this quartic should be PSD at that point. So if we can somehow show this stronger result, we would be done. And this is the last lemma of this one is lemma 0, which says that for a non-integer scalar k, 0 is the only second order point of this quartic polynomial. So in fact, no other point is even a second order point, so it cannot be a local min. 0 is the only second order point, but we separately show that 0 is not a local min, so we would be done. Okay, so now the goal is to prove lemma 0, which is very easy to state. Is if you have a non-integer k and you construct this polynomial of degree 4, no point in Rn no, 0 will be the only second order point. Okay? And this is where it gets kind of interesting. So I'm going to need some notation. So for two vectors A and B, or for two matrices A and B, this notation is the entry-wise product. Okay? And I need some other notation here. So if x is a vector of length n, x bar is also a vector of length n, M is a symmetric matrix n by n, and G is a graph on n nodes. This notation is a restriction notation to the support of x bar. So let's think x bar is a vector of length 10, but it has 3 non-zero elements. Let's say entries 2, 5, and 7 are non-zero. Right? Then this x sub x bar will be a vector of length 3, which has, in those 3 entries, has entry 2, 5, and 7 of x bar. Right? Similarly, M sub x bar will be a 3 by 3 matrix instead of a 10 by 10 matrix, which is a principal subblock. So it has rows and columns indexed by 2, 5, 7. And finally, G of x bar will be an induced subgraph. So you take just these 3 nodes in your graph instead of the 10 nodes. You keep all the edges between these 3 nodes, and you throw everything away, everything else away. Right? So this is what this notation means. OK. So what am I going to do with this notation? So we want to prove 0 is the only second order point. So let's compute the gradient and Hessian. And I want you to trust me on the algebra. So you can do, so with this notation, this can be conveniently written like this. You can do some sanity checks. So if P has homogeneous and degree 4, the gradient should be homogeneous of degree 3. And it is. And the Hessian should be homogeneous of degree 2. And it is. So this notation creates a diagonal matrix out of a vector. That's what this means. Okay. And now let's see. So suppose, for the sake of contradiction, that there was a non-zero point x bar, which was a second order point. Okay. Now at this point, the gradient should vanish. But let's look at what happens if the gradient vanishes. And if we plug in x bar, and then we restrict this vector to the support of x bar. Because it's an entry-wise product, if the entry-wise product is 0, that means on the entries where x was non-zero, this other vector should vanish, right? So this is what this says, that this other vector, when restricted to the support of x bar, should vanish. But that simplifies the Hessian, so I'm also going to evaluate the Hessian first at this point and then restrict it to the principal subblock given by the support, and the second term will go away because of this, right? So the Hessian, when restricted and evaluated x bar, will be this expression. Because the Hessian has to be PSD, its principal subblock needs to be PSD. And this implies, by a simple linear algebra argument, that MAK sub x bar is PSD. So this is the only thing we need to remember from this slide, that if there is a second order point, then I can take this matrix MAK. So a reminder of what's the definition of MAK. I can write MAK based on the graph and the k, which is non-integer. So this matrix as a whole, it may not be PSD. It may not even be copositive. But there is a principal subblock of it, which corresponds to the support of x bar. That subblock will be PSD. OK.
Why did the diagonal matrix?
Because of this. Because this is diagonal produced by this vector. And this vector is literally 0. Sorry, I know the notation is a little hairy now, but it's the last slide with heavy notation. So, okay. So now so we established that this principal submatrix is PSD. Now the other very natural thing to do is let's look at the graph restricted to x bar. So let's look at the induced subgraph gx bar, which I only pick the nodes where entries of x bar are non-zero, right? And I can play the same game. I can write this matrix for that smaller graph. It will be a smaller matrix. And it's easy to see that that's the same as picking the old matrix because of this definition and restricting that matrix to x bar. This is what on the previous slide we showed is PSD. But that implies that the M matrix for this smaller graph is PSD. A PSD matrix is definitely copositive. And if I'm copositive by lemma 1, one more time, alpha is less than k. So for the smaller graph, alpha is less than or equal to k. Okay. Oh. Now, there's one more nice property that this matrix has. It is PSD, but it has an interesting vector in its null space. In particular, x bar squared restricted to the support of x bar, right? So in the first equality, I'm just replacing this matrix by that, right? In the second equality, this is just some algebra on how you can distribute this restricting operation. And the last equality comes from the previous slide that the gradient vanishes, right? That's the question that Daniel asked, right? But why is this interesting? Because if you look at now this quartic polynomial restricted to this adjacency matrix, so this is a quartic polynomial in fewer variables, right? In the variables in the support of x bar, this has to be 0 at this vector because this polynomial is nothing but this vector multiplied on the left by the same thing transpose, by x bar squared x bar transpose, right? Okay, but that means that this polynomial is not positive definite because it vanishes at a non-zero point. And one last time by this lemma, the counterpositive, I have that alpha of this smaller graph is more than equal to k. So the opposite inequality. You can probably see the contradiction. So this has to be equal to k, but k was not an integer, and the stability number is an integer. Right? So that's a contradiction. So what did we establish? We succeeded in proving lemma QU, quadratic on constraint. So if you have a quartic polynomial, is NPR to test if there is a local mean. Okay, so now we're done with quartics, and I want to go back to quadratic programs, and this will be more straightforward. So now I want to go back to this notation of the Q, which is a quadratic form, right? And the first lemma, I'm going to call it lemma E for existence of local minima for unbounded QPs. And it says it's NPR if you have a QP over a unbounded set, unbounded polyhedron, to test if he has a local min. And the reduction is very straightforward. So you start with the graph and n vertices, and you want to test if alpha is more than or equal to r. Once again, you subtract a half first. So k is r minus a half. And now you put in your objective the quadratic function qak, which is on the slides. And we just proved that alpha is more than r if and only if this quartic function has no local min. But it's very easy to see that this will happen if and only if this quadratic program has no local min. Why is that? Because for any point x which is feasible, x would be a local min for this QP if and only if the entry-wise square root of x will be a local min for this quadratic function, right? Because it's easier to see the counterpositive of this. So for instance, if this x is not a local min for this QP, that means there is a sequence of points approaching it which are all feasible, all non-negative, but having value less than at your candidate point, where you can take this sequence, which is the square root of the previous sequence, and that sequence will converge to square root of x and contradict that square root of x is not a local min, and this goes in both ways. Right? Okay, so the thing to remember from this slide is that we can also check if alpha is more than r by checking whether a quadratic program has a local min. Once again, you subtract the half and you put that in the objective. Okay, and now I'm finally back to the main theorem. Remember, the question as proposed was that you need the feasible set to be compact. So when the feasible set is compact, you cannot, it doesn't make sense to ask, is there a local min or not? Because the answer is always yes, right? So now this is a search question. It's just about finding this local min. And I already gave you the reduction at the beginning. Now I'm going to argue why the reduction is correct. So this is the objective function. The 1/2 has already been subtracted. So k is r minus 1/2. And let's see why this works. Okay. So if you have this quadratic program, and remember, I claimed that if you had any algorithm that then went within distance 2 to the n or c to the n of any local min, that algorithm would decide which case you're in. Is alpha less than r or more than equal to r? Right? And that would be the end of the reduction, right? So the reason this happens is that if alpha is less than r, I can claim that the QP has a local min, which is at the origin, of this, and this is the unique local min. Why? Because if alpha is less than r, then alpha is an integer. It has to be less than r minus a half, right? Which implies that this quartic form would be positive definite. One last time, this is by this, right? So which implies that this objective function is strictly positive on the feasible set. So you're 0 at 0 and everywhere else positive. So 0 has to be a local min. Why is it the unique local min? Where if you, let's suppose you had another local min, then if you draw the line to the origin, because you're positive here, the quadratic function on that line looks like this. So if I multiply my point by like 0.9, it's going to take a smaller value. So it cannot be a local min because that's the descent direction. So this is the unique local min. OK, what about the other case? If alpha is more than or equal to r, then I claim that all the local minima have to be on this orange line. So there could be multiple of them in this case, but they all have to saturate this last constraint. So why is that? That's because of the proof of the Lemmae, the unbounded QP, because we just proved that if alpha is more than r, if you remove this last constraint, there are no local minima. That's what we proved, if you remember, right? So now that the feasible set is compact, there have to be local minima. What choice do they have? They must be on this line, because if they were anywhere else, let's say they were here or in the interior, then there would have also been a local min for the entire non-negative orthant. And that we ruled out. Right? So all the local minima have to saturate this constraint. OK, so now we're done, because suppose there was a polytime algorithm that, given any quadratic program, landed within distance c to the n of one of its local minima. So take that algorithm and run it just on these quadratic programs. What is it going to happen? So on these quadratic programs, the local minima is either at the origin or they're here. The distance from the origin to this line, and this goes to your question, is 3 times c to the n. So if the algorithm is going to be within c to the n, is never going to land in the white area. So that comes as a guarantee, because it always has to be within c to the n of some local min. So if the local min was here, the algorithm would end up somewhere here. If the local min were on the orange line, the algorithm would end up somewhere there. Well, we can run the algorithm and then see where it lands, and based on that, reverse engineer this and see, OK, are we in this case or in that case? Right? OK, so the wrong direction. So this is the end of the proof. And to recap, so we had this lemma m, which is on the board, and we proved it many times. To prove lemma 0, which is that 0 is the only second-order points of these quartic polynomials. And that allowed us to prove the non-integer lemma, which is that if k is non-integer, and this was important, then we can relate the stable sets to local minima of these quartic polynomials. And this allowed us to prove that for an unconstrained quartic, testing local minimality existence is NP-hard. This allowed us to prove lemma E, which is about existence of quadratic programs in the unconstrained case. And finally, the theorem. And the reason I recap this, in case you haven't noticed it, is that as many theorems in polynomial optimization, there is an influence by Monique. And in this case, it's very direct. But sort of more seriously, I want to use the opportunity to thank Monique for. OK, yeah, this took me a while to engineer. So I think the first time I met Monique was at this workshop at the Wolfpack, where it was about an SDP workshop where there were 4 instructors. Frank is also here, and at that time I was a graduate student at MIT. I don't know if you remember, when we had problem set sessions after the talks every day, and I remember Monique's problem sets were very difficult, and she would give no hints. So at the beginning, our relationship didn't go so well, but that has changed over the years. I'm joking, of course. And this is our last encounter was from last week, where Monique came to Princeton and gave 2 fantastic talks. So congratulations on becoming a fellow here and on all your amazing lemmas and theorems. So I'm not desperately short on time, so I'm going to. I may not get to the last part, but let me. This is more of a discussion slide, which I sort of found interesting as I was making the slides. So because if you see this theorem and you came with the mindset that, okay, of course, local minima should be easier to find than global minima. And now here I am telling you, no, they're not. And not only they're not easier, you cannot even get exponentially close to them, right? So your reaction may be that, okay, but maybe this is the worst case result. And, NP hardness doesn't happen in practice and things of that sort. So I want to discuss this a little bit by making a few observations. So first of all, there are a number of results in the theoretical computer science community that say if you have any NP hard problem, that it cannot be that the only hard instances are a few, like this, and this can be formalized. Then let me just say what this implies for this problem. So an implication of this result plus these other theorems is that if you pick any polytime algorithm which attempts to find the local min of a quadratic program, so let's say this is the gradient descent algorithm with projection to the polytope, or is some sort of semi-definite relaxation, any algorithm, as long as it runs in polytime. And now you can see, okay, out of all the instances that I can write down with k bits, so there will be 2 to the k such instances, on how many of them will this succeed and how many of them will it fail, right? And all the 2 to the k instances, this algorithm must fail on a number of instances which is larger than any polynomial in k. So you cannot bound the hard instances by a polynomial. So there will be some large super polynomial number of instances where your algorithm not only will not find the local min, but it will land exponentially far from any local min. At the same time, I find this other claim contrast interesting. And this is when you study things in sort of the real model and you ask genericity questions versus NP hardness results, right? And I cannot make this connection for the problem that I described, but I can make it very precise for a simpler problem, which I had on my beginning slide. This is the result of Mordi and Kapadi, right? So if you have a quartic polynomial and a point, this is a recognition problem, is NP hard to check if x bar is a local min, right? This I had on the first slide. Hence, by the same claim that I told you, any polytime algorithm would fail on a large number of instances, on super polynomial number of instances. Yet, for a generic quartic polynomial, so if you generate p randomly, let's say, then a point is a local min if and only if it satisfies the gradient vanishes and the Hessian is positive definite. And this can be checked in polytime, right? Because this you have n leading principal minors, right? So where is the catch? So the catch is that we are in completely different spaces, right? So when you implement these questions on a computer, you are not in the real space, right? So the inputs are rational. So all the inputs have measure 0 in the set of all real inputs, right? So within this measure 0 set, we're counting a subset. How many of them is your algorithm succeeding, right? So there is no contradiction here. And in a way, this sort of saying that these problems are generically easy, they only apply if you had a real machine computer, not a digitized computer where you were implementing the algorithm on with floating arithmetic and rational numbers, right? And there are other theorems in our community like this, like a very well-known one is this really nice result of Jiawang Ni, which says that under the Archimedean assumption, so this is more for the experts, I apologize if you're not familiar with this, the Lasserre hierarchy has finite convergence generically, right? But this is sort of the same situation. What if we run the Lasserre hierarchy on a digital computer, which we do all the time, right? And the input is rational, then the statement doesn't tell us, on how many instances you will succeed or fail. And to my knowledge, the complexity of testing finite convergence is not known or anything of that. So I think it's best if I completely skip the last part of the talk. So I apologize for that. But the last part I was actually more positive. There's a positive result about cubic polynomials where you can find you can both solve the recognition problem. So if you have a cubic polynomial, you can test. And why cubic? Because this is sort of the only case left in polynomial optimization, if you think about it. So you can solve the recognition problem given a point, is it a local min? You can also find the search problem given a cubic. Tell me if it has a local min, and if so, return one. You can do this with semi-definite programming. And sorry for the mistiming, but let me just go to my last slide. and tell you that if you're interested, this is the second paper is about the cubic polynomials. Thank you.
So there's definitely time for questions. Anybody?
It seems to me that the quadratic example you construct has that exponential in the bit in the data. So what is the relation to the bit size?
No, that's fine because okay, so it's a good question. So let me go back because the claim is that if you have a polytime algorithm for any quadratic program, right, that would get within exponential distance of a local min, then p equals np, right? So that statement is true independent of like what quadratic program I wrote down, right? So that is just a proof technique because I can show that I can give a polytime reduction. So you're right that you get the exponential result if you put this number here, right? But the fact is that you can write this number in polytime. And so there's no issues with putting this number here. But you can put any other number here, like Danielle said, you can put an n here, right? And you can ask, okay, if I restrict myself to even more QPs that maybe all their magnitude of all these entries are bounded by the dimension. That would be a separate question, right? And what this reduction would tell you that you cannot then get within, I believe, root n of a local min, right? But the statement I said is correct. If you consider all QPs, you cannot get within 2 to the n of any local min. But if you put further restrictions, now only want QPs who numbers are by magnitude bounded by n, then this will no longer be a valid reduction, but you can put n and then you get that you cannot get within root n. That's also in our paper as a corollary.
Is it all that if P is NP, that is a polynomial algorithm?
If P equals NP, that's certainly for stable set, but I'm not showing completeness here, right?
Yeah,
so
for any matrix, this is for any quadratic program. Or
So if P equals NP, can we find local minima in polytime, right?
yeah, or
so
at least the question you posed there,
yeah, no, I because here I'm just showing NP hardness. I made no statements about completeness or membership in NP.
Yeah.
So it doesn't follow. It could. I mean, I believe it would, and I believe P is not equal to NP. But hypothetically, it doesn't follow directly, right? Because I haven't shown that this problem is in NP. But hold on. But the copositivity problem would be solved, and the recognition problem would be solved.
But it is for any quadratic program,
Yeah.
This, not just for copositive programs.
Yes. So that's why I don't see. So if P equals NP, can we find a local min of a?
Can you find with small bit size? I guess, that's the question then.
Yeah. So such a thing would always exist, and I don't think it would. Would it follow that? Yeah, actually it would follow, right? Because of Avasis's result, right? That there is always a certificate of small bit size, right?
Oh,
So
yeah,
Vavasis says quadratic program is in
yeah.
NP. So of course,
Yeah,
if P equals NP, then quadratic program is in NP.
Yeah.
Yes. So not by this, but by Vavasis's
And you
theorem.
can certify that it is a minimum then.
Yes,
Yeah.
yes, but nothing by what I said is by a result of Avasis.
thanks.
The
Yeah,
title of the
yeah, you're
paper
right.
is QP is in NP.
Yeah.
Yeah. Sorry, I got confused.
Actually, yeah, can't stop myself from asking a question. Sorry. So, in the generic case, it's still not clear whether you can certify that a local
Whether you can
minima-
find local min.
Yeah, or that it exists. Right?
No. So that's why I only made the connection to the recognition problem.
Like for a specific point.
Exactly.
Yeah.
Exactly. So
So it
in
could
the
still-
generic case, is that's true? Where was it? But even in the generic case, I don't know how you would find the local min generically.
All right. So if there are no more questions, let's thank Amir one more time.